All right, so today we are headed into working on Le Chatelier and working on calories on a little mini lab that we're going to do in here. We're also going to cover some of our notes, so if you'll grab your notes out and we'll take little breaks and do these little mini labs in between. Okay, so you'll just be working with somebody anyway, so we've got Ch6 next one right here. Okay, we're going to talk about spontaneous and non-spontaneous. We're going to go through a few of the vocabulary words that we need to know. Okay, here we go, guys. I know everybody's excited for break. Me too. Let's get done what we need to before we go to break. Okay, which of the following are spontaneous? Is this spontaneous?
Yeah.
Okay. Is this spontaneous?
Does not look
Absolutely.
Is this spontaneous?
No. I can't find the spontaneous.
Is this spontaneous?
Yes.
Oh, what's spontaneous?
Things that when it moves fast.
Things that require
Things that appear for no reason.
are like things that will go on their own.
There we go. Things that will go on their own. So if I drop a ball at the top of the hill, it's going to roll down. I don't have to do anything but drop the ball. Right? But to hike up a hill, I have to put effort in, put energy in to get up the hill. Push a rock up the hill, I've got to put energy in. Push that rock up the hill. Ski down the hill, all I got to do is step on the skis, right? Only me, it would be like a big snowball that comes up the end. Okay? All right, some of the words that we need to know. Exergonic. What did I tell you last time exergonic was?
It's like exothermic.
Exothermic. So it's giving off energy, the release of energy. Okay, it doesn't have to be thermic. That's the thing. Exergonic means energy is given off. So it could be in the form of light or sound. Okay, exothermic is just heat. Okay, what about endergonic? Takes energy in. So it could be in the form of light or sound or whatever, but it's when energy is taken in. Okay, it can be metabolic or it can be chemical. So, all right, then we've got entropy. We talked about that a little bit last time. I told you about my kids' rooms. They tend to head to total entropy. Entropy is the lack of order or predictability. Okay, the universe is said to be headed towards total entropy. Yes.
Will we talk about thermodynamics in this class?
This is where we're talking about, but not really in depth.
I'm learning about this in 2 classes now.
Woo! Double whammy. Okay, so what is that about a stable substance? What is a stable substance?
Something that's not gonna react.
Something that will react or that won't, that's already at its lowest energy state. Okay? So I'm already at the lowest energy state with its environment. Okay? So we've got a few words that we need to make sure that we understand, we know the meaning of them, and we'll need to be able to use them in referring to different scenarios. Okay? So if something is giving off heat, I'll call it exothermic. But if it's giving off energy, then it would be, oh, excuse me. Where did I put that? Hello?
Like you could sell the CEO of Ch6. No. Yeah, no.
Okay, so back on this, sorry about that. We We need to be able to understand these when we use them back and forth. Okay? Okay, go forward.
1 second.
No,
You don't have to have it word for word, just main idea so you know how to use it in a sentence, you know how it's used in a sentence. Okay, so when looking at this, hint, hint, this might be something that might be on. You need to be able to classify them as endergonic or exergonic. Okay, so any combustion process. Exergonic. Okay, perspiration evaporating from the skin. Okay, watch this. Perspiration evaporating from the skin.
Oh, then yeah,
It's the perspiration. So what's happening to perspiration? Is he going in or coming out of perspiration?
In.
No, it's
In.
Aha!
Going in. So the perspiration is getting heat put in, so it turns to steam or comes off, right? So it's endo. Okay, you gotta look at how she's worded it. Perspiration evaporating off the seed. So you're putting energy in to make that perspiration evaporate. Come on. Energonic, sorry, but it is endothermic too, because it has to do with heat. Okay, what about this next one? Melted lead solidifying. What's happening to the lead? It was liquid, it's hot, it's getting off heat, so off energy, so it's exergonic. Any explosive detonating. Exergonic. A car being pushed uphill from the point of view of the car. Endothermic, good, because the car is getting energy put into it. Okay, so you got to be careful how she's wording this. This is why I put a few of these up here. You need to make sure you understand. Now, if I just said the skin, when perspiration is evaporating, the skin becomes cooler because heat is being taken from it. So that is exergonic. Okay, but the perspiration, the liquid on top of the skin, as it evaporates, it has the skin heat put into the perspiration to make it go up. So it's endergonic. Okay, so be really careful on those types of questions on the test because she can flip it by just putting the point of view differently. Okay, so be careful. Okay, so exergonic, we decided endergonic. I forgot I had these on here, exergonic and endergonic. Okay. Describe the energy and the entropy. Okay, so energy and the entropy. Changes that occur in the following processes. On a cold day, water freezes. What's happening to the entropy? Decreasing because it's becoming more ordered. Good. And what about the energy? Endergonic or exergonic?
Endergonic. No, wait.
Exergonic.
Exergonic. On a cold day, water freezes. I'm looking at the water.
Because the heat's
Heat's leaving,
Yeah.
so it's exergonic. Good. Decreased energy, decreased entropy. So when we decrease energy, we're going endergonic or exergonic. Sorry. A container of water at 40 degrees cools to room temperature. Decreased entropy, good, and decreased energy, which would be exergonic, good. Okay, and the bottom one, the odor from an open bottle of perfume spreads throughout the room.
increased
Increase entropy and
Increased energy, because it had to have energy to move around.
Wait, so is it always going to be the same? Like decreased and decreased?
Not necessarily. There are times we change them. Okay, but you got to look at what's going on with the option. Okay, so classify each of the following as spontaneous or not spontaneous. This is going to happen on its own. Yes, ma'am.
So on the test, will it say like describe the energy and entropy, or will it be like
It can do
determine
both.
which one?
They can do both. Okay, all right, so this one we're going to classify as spontaneity and non-spontaneity. Okay, water is decomposed into hydrogen and oxygen gas by passing electricity through it.
non-spontaneous.
Non-spontaneous. Why? I had to put electricity into it, had to put energy into it. Okay, an explosive device or explosive detonates after being struck by a falling tree? Non-spontaneous, good, because I had to put some energy into it. That tree falling was that energy. A coating of rust forms on a clean piece of iron. Spontaneous, it's going to happen. Okay, if I don't do some protecting. A flashlight emits light when turned on. Good. Whipped cream dissolves on a hot piece of pie. Yeah, happens every time, right? Okay, and I didn't have to put any effort into it. All right, so you need to be able to look at things and be able to say if they're spontaneous or not. Okay, here we go some more. Each of the following are organized according to the highest entropy. Or organize each of the following according to the highest entropy. Lowest entropy. So most disorder to least disorder for each of these. So solid ice, liquid ice, and steam. What's the highest entropy? Highest amount of disorder? Steam. So steam would be number 1, right? So steam would be number 1. What would be number 2? Liquid water, and then solid ice. Okay, looking at the next one. Leaves on a tree, leaves fallen and blown about in the air, leaves fallen and right onto a fleece paste on a sheet.
Blown about on the tree.
Blown about is the highest entropy. Okay, then what?
Great.
Okay, and then leaves on a tree. Good. Okay, next one. A stack of sheets of paper, a wastebasket full of sheets of paper, a wastebasket full of torn and crumpled pieces of paper.
Would it be one?
Okay, torn and crumpled, number 1, then, okay, and then a stack. Okay, a 10% zinc copper alloy, 2% zinc copper alloy, or pure copper. Which is the most disordered? 10%. Okay, and then?
Wait, why is that?
And then
Pure copper, so it's 10%.
10% means you have more of them that can be arranged different ways in there.
Wait, so that's the least?
This is the most disordered. This is the next disordered. And this is the least disordered. Because this only has a few flecks in it. So it can be around here and here. But if I have a whole bunch, I can have a whole bunch here or here. Yes.
So does that mean like would a 100% zinc alloy be the most disorderly, or would it?
Well, you wouldn't have a 100% zinc alloy, right? Well, theoretically, I guess you could, but it would be 50% copper, 50% zinc, right? To be honest. When it says an alloy, there's other things we can put in there. Yes.
Wait, but haven't this entire time we've been doing 1?
Yeah.
Is that
So
highest
would it
entropy?
this time be? So first one would be 1.
Okay, if you look at it like this, you have 100 things, and you only have 2 in here, right?
You just know
This one you have out of the 100, you have 10.
No, we get that.
Yeah,
Just
remember,
like
we
label
get
it
that
wrong.
usually,
Yeah, label it
but the
wrong.
most disordered is 1.
Right, this would be the most disordered.
Wait,
So
but
what
three,
is
what's
it?
3?
Thank you. Not understanding, sorry. Okay, last one. You guys decide, what's what? We're not gonna rate it.
Same coins is 3.
Ten coins is 1 or 3?
Would coin even be the most
Well,
disordered?
because if it's the same time that they're the same type, that's kind of like copper, isn't it?
So we've got coins, we're figuring just a bunch of coins. We have coins in piles containing the same number of coins, or coins in piles containing the same number of coins.
They're the same type of coin and the same number of coins.
Right.
So,
So they
the
could be
type of
different
coin
numbers.
would be 3.
Would be the most ordered, right? So that would be 3, yep. And then what?
And then would the coins in a piggy bank be 1?
Actually, this would not be the most, that would be the most ordered, right? That's what we're doing. Most ordered,
So 3 would be the most.
okay, and then 2. No, that would be,
No, yeah, I was.
yeah. And then 1. Okay, we good? All right, going forward. We did a lab last time on reaction rates. We're going to do another kind of lab today with reaction rates over time with 2 things happening. Okay? where we have reactants and products happening at the same time. When you start a reaction, you just have reactants, no product, right? Over time, you're making product, you're losing reactants, right? Are you okay with that? Okay, so what we're going to do is we're going to graph a rate of reaction, okay? Only on ours, we're going to do a little bit different. We're going to start with some product because we know now that it's not just a one-way reaction for a lot of things. Sometimes it goes backwards. And we reach what's called a point of equilibrium. Okay? So it's basically that we need to know the change in the reactant over change in time. Okay? No matter what we're doing. So if we're getting rid of it, it's going to have a negative in front of it. If we're producing it, it becomes a positive in front. But it's always change of whatever product or reactant divided by change in time. So we're taking two places. You guys know this as slope, right? So all I have to do is find the slope wherever reactions take place, whatever time I am on the reaction. When we first start reaction, it's going to go faster than later on in the reaction, or when it has come to a point of equilibrium. Okay? Rate is equal to slope. If it's going backwards, if I'm decreasing, if I started with this concentration, it's now reacting, I'm going to end up with a negative slope. Okay? If I'm building it, if I'm producing products, I'm going to end up with a positive slope. Okay? All right. So, now you got to think about this. Is this reaction going to be fast, very fast, slow, or very slow? You're talking about rate now. Melting of butter in a hot pan.
Fast.
Okay? Change of the color of leaves in the fall.
Very slow.
I would probably say slow. I'm thinking very slow is many millions of years.
Oh, okay.
Okay? The growth of the garden over the summer.
Slow.
The decay of radioactivity of a material whose half-life is 4 billion years.
Yeah.
Very slow. Okay, detonation of an explosive once triggered.
Very fast.
Okay, so you know the rate. You should be able to look at stuff and be able to use your knowledge to determine what the rate is going to be. Okay, you should be able to grab stuff like this. It's very simple. What did I tell you? The change in concentration of whatever you got divided by the change in time, right? A and B are mixed. After 12 minutes, what's that? My change in time. Okay? The measured concentration of C, remember we didn't have any product to start with, is this. So what is this? My change in concentration. I'm just going to call it C.
Wait, what is triangle?
Change. Means change. Okay, so remember my rate is going to equal my change in concentration over my change in time. Very simple. What do I do? 0.396 divided by 12 minutes, and it's molarity divided by minutes, and I'm going to end up with molarity per minute, which is going to be my slope at that point. Okay, what is it?
0.33.
0.32? Should be less than that, isn't it? This divided by 12? 0.033. Okay. All right. On the bottom here, we've got concentration of pure A, B, and C are mixed together at equal concentrations of 3 molar. Now this is where she gets a little tricky. So each of these started with that. That's not my delta, that's just the starting point. After 8 minutes, so this is my delta T, right? The concentration of C is found to be this. How do I find delta C? Subtract them. Okay, so I got 0.455 minus 0.33 or 300. That's going to all be over my 8 minutes. And this is molarity on top. I plug that through and I get, I shouldn't put delta there, I should have put rate. Rate again is going to equal delta C, change in C over change in time. What do I get? 0.019. Okay. And this is molarity per minute. Don't forget the units.
Wait, what is that?
Double check.
Above the
Like the triangle.
Oh, it's delta.
delta T
Means change.
Okay.
change. Okay, these should be really simple, easy things, okay? To be able to calculate. Anybody having problems with it? Yes.
Do you always subtract, not subtract, like the,
You're always going to divide the concentration by the time, and it has to be the change in concentration divided by the change in time. So they could say from minute 12 to minute 19, you have to subtract that to get the delta T. Okay? Very simple, just remember concentration over time. Change in concentration over change in time. Okay, that's rate. We all right? Now be careful, because if this had gone to 0.1 molar, it's decreasing in concentration, so the rate will be negative. So if this right here, instead of being 0.455, which it increased, right? If it had gone down and become 0.1,
Or like 0.2 or
yeah,
anything like that.
if it was below the 0.3, then my rate would have been negative. My slope would have been negative because I'm decreasing. And she won't tell you that. You just need to know that. So she'll have both answers on there, one positive, one negative. Okay, negative tells me what direction am I going. She's sneaky. Okay, so a reaction generates hydrogen gas as a product. Reactants are mixed and sealed in a 250 milliliter container. After that many minutes, this many moles have been generated. Okay, concentration. What is concentration? Okay, it was delta. I'm just doing C for concentration over delta T, right? How do I find concentration here? What is concentration?
Isn't it said 5.4?
It's got to be in molarity. So if you don't get it in molarity, you got to put it in molarity. Okay, moles and milliliters. Okay, so first off, I need to change the milliliters
Wait,
to
what's the
liters.
capital M stand for?
Moles divided by liters.
Like on the left hand side.
Molarity is equal to moles divided by liters. Okay, so I've got to change that to liters, so I'm going to take my 250 milliliters, and I know there's 1,000 milliliters in 1 liter, so I'm going to end up with 0.25, and it doesn't have a decimal, so I'm just going to take that as the liters. They gave me moles, so I'm going to put that here, 5.4 times 10 to the negative 2 moles. I'm going to divide it by 0.25 liters. What do we end up for the concentration? 2.16 times 10 to the what? Negative 4. Do I have a second on that? Somebody else do it real quick so we don't go through the whole thing. Find out we've got a mistake. I'm not saying you did it wrong. I always want to do 2 checks. Somebody else do it real quick?
I said that. Wait a second.
You started it. We're not going to have a second?
Wait, that's not just like that.
Come on, I need a check. You say here, wait. Calculator? Should be one of those things. Is that what you got?
I got that.
You got something weird.
That's not what I got. Not what I got.
Okay, what did you get?
I got 0.216.
Yeah, that's what I got.
Okay,
I don't know.
so, yeah, that's, so we got 2 and we got that, so it's not what we had up here, so there you go. That's why I was sort of wanting to have a check.
What may have happened is that you may have forgotten to put that decimal point in. I just want somebody to.
So you gotta make sure you put it in. Okay, now we've got the molarity, we've got the total time, right? The change in time from 0 to 15 minutes. So now we're just going to take, and this is equal to rate. It's not gonna let me write right there. That's equal to rate. So we've got 0.216 molar divided by 15 minutes. What's my rate?
.0144.
Okay, molarity per minute. So we had to do a little bit more work here to get it, but as long as I remember concentration, change in time, I can do it. If I know concentration has to be in molarity, moles per liter. Molarity, 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 moles per liter. Okay?
What?
What? Molarity, 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 moles per liter. It's a little bitty to help you remember. If it doesn't work, just remember molarity, moles per liter. I also look at it like this is a mountain.
Oh.
What's in the mountain? Usually a lake. So moles, mountains over lakes. Okay, whatever you want to do to help remember. Okay, going forward. Okay, molecular collisions. This is how does the reaction have to take place. So in the video that we watched of the school being shrunk down and we had the gangs of groups that we needed to crush up, the reaction mechanism says I have to be oriented in a certain way. Have enough energy when I meet with another chemical that the reaction takes place. If I don't have enough energy or if I'm not oriented in the right direction, the reaction is not going to take place. So particles must collide with another in order to form a reaction. I can't just have a particle, a chemical over here and say they're going to react. They've got to come into contact with each other. Okay, so they've got to meet. Second, particles must collide with the minimum total amount of energy if the collision is going to happen. Okay? We went sort of over this with that video. I'm just reviewing what we did. Okay, in some cases, colliding reactants must be oriented in a specific way if a reaction is going to take place. Sometimes it doesn't matter. If I have a chlorine and a chlorine, it doesn't matter what chlorine I bump into. But if I have a hydrogen and a chlorine and something else is trying to react with the chlorine, if it bumps into the hydrogen side, it's not going to do anything. It has to bump into the chlorine side. Okay? All right. So, internal energy is what I have in a system before any reaction takes place. So, my reactants have a specific amount of energy. My products have a specific amount of internal energy. The activation energy is the energy it takes to go from the reactants to the top of the curve where I'm going to actually have a reaction take place. We call this the activated complex at the top. That's when they are hit, but they haven't separated again. Okay, they've hit, but they haven't separated. In the video, it also talked about catalysts. A catalyst is like a matchmaker. It gets things together, orients them correctly, gives them enough energy that they can react. Okay? That is always shown by a lower activation energy. It doesn't necessarily have to be smooth like this. It could be going like this. Okay? Because it goes through a different mechanism in order for it to work. You will need to be able to look at this kind of graph and be able to label it. So this is what we call activation energy, E of A. This right here is the activated complex.
What's the
Activation energy. The distance between my reactants and where my products are is my delta E, or change in energy. Sometimes they put delta H there if it's an exothermic or endothermic reaction. But if it uses different forms of energy, they use delta E. So I'll put delta H here as your alternate. Okay?
Wouldn't it be AE instead of EA?
They call it EA, so the energy of activation. Okay, energy of activation or activation energy. They call it both, but the symbol is EA. Okay? And that's the minimum amount of energy it needs to be able to complete the reaction.
What's that red dot on the wall?
That is my activated complex. Activated. Okay. We'll be going over several more of these. You need to be able to label one of these, backwards and forwards. If it has numbers out here, you'll need to be able to take those numbers and tell me what is the activation energy, what is the and change in energy. Okay, where are the reactants at? Where are the products at? What is their internal energy of the reactants? What is the internal energy of the products? That's just reading the graph. Okay, so there's a couple of problems like this. If you understand this graph, they're way easy on this test coming up. Way easy. Okay, so which reaction mechanism assumptions are apparently being violated in the following scenarios? So think of all that you know and listen to this. A reaction takes place more rapidly when the concentration of the reactants is decreased. What you did last time, what does this not make sense with? That statement. So you did 3 reactions last time. You tested one with concentration. What happened when you decreased the concentration of one of them? It happened slower. So if this right here is not right? It happened more slowly. Okay, let's look at the next one. So she's looking for you to correct misconceptions on this kind of question. Okay, the second one says, a reaction takes place more rapidly when a reaction mixture is cool. It would be slower because when you put stuff in that was cooler, it slowed the reaction down. So again, here, slower, or they could have changed this to heated, right? So there's 2 ways we can change that to make it correct. Okay, the bottom one. The reaction rate of A plus B, yielding AB, increases as the concentration of A is increased, but does not change as the concentration of B is increased. Okay, let's put this one away, please. What's wrong with that sentence? This is a 1-to-1 ratio, right? So if I increase one, I better increase the other in order for the reaction to go the same speed or faster. Yes?
Wait, wouldn't you decrease the other to make it even?
You could, but it says it increases, so I either need to change that to decreases, or I need to do something different. So there, she's looking for you to look at the phrase, and this is the reason I had you do the lab last time. Because you had hands-on now experience, and hopefully it's stuck in your head. We changed the temperature. We changed the concentration. We changed the particle size. All of this has to do with that. Does that make sense? Now, I didn't have you write it up, but you might want to write down your thoughts of what you actually found out, right? Okay, so everybody okay with this one? These need to either both increase, or if one of them decreases, then the reaction rate's going to go down because we're going to run out of one. If one of them goes up, this one becomes limiting. I'm going to run out of it anyway. So we'll go the same speed. Okay, the energy diagram. Again, you're going to go through and you're going to label all of this. It will have numbers. Okay, so if she asks you for the activation energy, that is the distance between here and here, right? So you're going to take 103 minus 15, and you're going to actually get some amount of kilojoules for the activation energy. And if we do that, my brain, somebody help me because my brain is not working very good today. So then 93.88, yep. Okay, if I want to find the distance of my delta H, because kilojoules is heat, the delta H here, I would take 15 minus 10, I think I can do this one in my head, 5 kilojoules, right? If I need to label where my reactants are, I say they're right here, and
Wait, so what's delta H?
delta H is the 15 minus the 10. The distance between the reactants and the products. If they want to know what the energy of the reactants are, it's 15. If I want to know what the internal energy of the products are, it's 10 kilojoules. Okay? If they ask me, and they won't ask me to draw, but they should show me a thing and draw in a dotted line, something like that, I would say this is the result of what?
Catalyst.
Catalyst. And what does a catalyst do?
It speeds up the reaction.
Without taking in the catalyst.
lowers the activation energy. That's important that you remember it lowers the activation energy. It might not speed up, usually it does because it takes less energy, but it doesn't necessarily. But it does lower the amount of energy that's needed. That's important. That's what our enzymes do in our body. If we didn't have enzymes in our body or catalysts in our body, we wouldn't be able to function. Because it would take too much energy to do all the equations or all the chemical stuff that we need in our body. Okay, E of A prime is just if I go backwards. If I go from my products to the top of the curve, that's my energy of activation of the reverse reaction. So if they asked me for that, I would take 103 minus 10, and I would get 93 kilojoules as my E of A prime. So anytime they put a prime on it, it just means how much to go backwards. So here we would actually be giving off 5 kilojoules. Going forward, we would be overall change of adding 5 kilojoules. Okay? Make sure I put everything in there. Again, your activated complex is up top. I'm just going to call it AC and refer to right here. That's what that is, activated complex. What?
Delta H was positive in this case, right?
Delta H going forward is negative because it's being given off. Going backwards is positive. So you've got to remember a positive in front means I'm putting it on the reactant side. If it has a negative in front of it, it goes on the product side. So over here I have less, right? So I need to have a negative in front of it, so it will go on the product side. So this is delta H. Okay. So if it's negative, so this one, the change is 5. If I'm going for this way, delta H becomes negative 5 kilojoules. If I'm going this way, delta H is equal to a positive 5 kilojoules. We usually don't write the plus, but you can. Okay? Because I have to add 5 kilojoules in to get here. I'm taking 5 away to get to here. Are we okay? All right. We've got another one here. You should have it in your notes. I want you to take time and try and label everything. Give me all the numbers on this one. While you're doing that, I'm going to pass out a candle, and I'm going to add a scale, and I'm going to have you start weighing the candle, and then we're going to light the candle. So do this in pairs of 2 or 3.
But what happened to the big jumbo candles?
What about them?
The ones with like kerosene on?
Oh, those are candles. Those are birthday heaters. I'll just give you guys one here. Stupid watch. Oh, yeah, as soon as I pass this out, go ahead and weigh it, and this is on the candle one. Share it with a neighbor, whatever you got to weigh. The battery's dead.
Oh no, wait. I think you're right.
because I'm gonna turn around and light them. I'm gonna let them burn for about 5 minutes. So we're doing some other stuff.
Wait, is gasoline the catalyst for fire?
That was very sad.
I don't know that I called catalyst for fire now. Okay, how many are done labeling? You still need a minute or two for all the labeling? You guys wait? Wait.
It just keeps decreasing in weight. It's starting at below 13.
You guys wait? Okay, so set a timer for about 5 minutes. You don't want to wait right after we blow it out. So somebody set a timer for 5 minutes. All of them are lit right now.
We need ours to be lit.
Almost all of them are lit right now. Okay, let's see how you did as far as labeling. This would be your reactants. It would have internal energy of 50 kilojoules. This is your products. It would have an internal energy of 100 kilojoules. Delta H here would be a positive 50 kilojoules for the forward reaction, and negative 50 kilojoules for the reverse reaction. The E of A here would be 250 minus 50, which is 200 kilojoules. E of A prime would be 250 minus 100, which is 150 kilojoules. And the activated complex would be 250 kilojoules. Okay? We should be able to label all of that. Now, looking at the graph, is it exothermic or endothermic? Yeah.
Wait, so which one's E of A and which one's E of A?
E of A is here, this is E of A prime, sorry.
Okay.
This one is an endothermic. Because I end up with the products higher than the reactants. If the products are lower than the reactants, then it's exothermic because it's given off energy. If they end up higher, it's endothermic.
That's why.
Okay. Remember, when you add the catalyst, it lowers the activation energy. Okay, don't say it makes the reaction go faster.
Wait,
It
so it's,
lowers the activation energy. It can make the equation go faster, but we lower the activation energy. Okay, next one right here. You get to draw a graph given stuff. So she would give you the information and show you several graphs and say which one is correct. So we've got a 30, we've got a 50, we've got an activation energy, we've got a negative 20. So I need to at least start at 30. Let's go 2, there's a 10, there's a 20, whoops. Here's a 30, 40. Okay, I want you to try and write it in. I'm just starting to give you an idea of what you could do to. Okay, go ahead and draw what you think the graph's going to look like. It's got to be to scale. So potential energy is like the energy, internal energy. Just another name for it.
Pile.
Potential is like the internal energy. So the reactants, so the internal energy or potential energy of the reactants.
So that's
How much energy it has.
start with, so it's your
So it starts at 50.
Starts at okay, guys, try this. Come on. Let's see what you can do. You're starting, I'm going to go really slow. You're starting with potential energy of 50. So that is your reactance.
How long? Oh, okay. How long does it stay at 50? Does
You
that
just
go
put
on?
it, yeah, you're not going to worry about time on the bottom. You're just trying to do this shape. I always like to look at where my reactants are. Then activation energy is 30, so I have to go up 30. So 10, 20, 30. So I'll come over here and just put a mark here. Because I'm going to have to make a curve to get up to that. And then delta H is 20 below where I started. So I go 20, 10, 20, come over here. And this is where my products are going to end. So then I just do a little arc here, go up, hit it, come back down. And it wants me to label everything. So here is my E of A. Here is my E of A prime. And from here to here is my delta H. Okay? How are we feeling with the activation curves? Okay, is this an exo or endothermic reaction?
An exothermic, right? Because the heat, by the time it hits the bottom, it's gone.
Okay, how many think it's endothermic? Raise your hand. How many think it's exothermic? Raise your hand. Yes. It is exothermic. The products are below the reactants. So this is exothermic.
Wait, what's the R accent?
Reaction. So when you get an RX, you're getting a reaction, chemical reaction. Okay. Change in energy, delta T, is another name for change in enthalpy, which is delta H. So change in energy is another name for change in enthalpy. Enthalpy is heat, so that helps you. And heat is represented by delta H. Okay, if delta H is positive, it means it's what type of reaction? I had to add heat in, which means endothermic, because it's working with the enthalpy. If it's negative, it's exothermic.
It's like, isn't that like exogonic, like general term?
Yes, because that can include light, it can include sound, it can include anything.
Okay.
That's energy. Okay. If you got your computer, or you got your phone, I don't know if it'll work on your phone, but once you get up to a simulation on rate, okay, all you have to do is go to set, and then you're going to go to heat energy, and you're looking for the one that looks like this. It's gonna make it bigger. You're gonna look for the one that looks like this. Okay, it's a rate experiment. We not have our computers out, do we? I'm looking, there's only one. Okay, so on your own, you might want to look at that one, okay? So it's a good one, and it also shows you, shh, guys, this also shows you the activation curve and how you are as far as energy. And it shows you how it works, backwards and forwards. You can mess with things. It's a good thing to go and play with for a little bit. Just like our lab last time, so it gets in your head how this works, okay? What you can do to make it go forward. What can you do to slow it down? Okay, so now we're going to get the graph of concentration versus time. We talked about this a little bit, and how the slope is our rate. The VR concentration is going to decrease over time. It's going to be used up. It's steeper at first. The more gradual the slope, the slower the reaction. The steeper the slope, the faster the reaction. Okay? We're going to be doing a little thing here with chemical equilibriums. We're going to try to figure out what's happening. Okay? This is at equilibrium, and this is at equilibrium. Why are they the same?
Because one's equal and one's opposite. One has
So,
equal
not
rates.
equal rates, but they're both at equilibrium.
Because they
Okay,
just fly
people,
oppositely.
the biggest misconception that students have is the top one, that it has to be like this on the top. They have to become equal in order for it to be at equilibrium. That's not true. Okay, the bottom one is actually more common, where we end up with a place where we have a zero slope. That's the definition of equilibrium, when my slope of both is zero. So we're going to play with this. Every group we need about 3 or 4 in a group. Okay, so get in groups of 3 or 4. You need to come up and grab one set that has a small beaker, and one set that has a big beaker, and one for each group. Okay? So you'll need 2 buckets per group. Come get them. It is great. Okay, we ran out of cans. I got buckets at the bottom. So you need one that has the graduated cylinder and one that doesn't. As you're grabbing it, I need somebody to take one of the cans over to the sink and fill it with water. Okay, so run over to the sink and get one of your cans. About 3/4 full of water. There's some on the bottom. So you need one of those. So go over to the sink and fill it about one of them 3/4 full of water. And then does every group have one? If you need more than 11, let's do that.
There's no more.
Okay, well, I'm gonna make my own.
Just get 2 buckets, get a large beaker and a small beaker, and I'll do that.
Right there.
Amazing.
No, we're fine. Yeah, let me just get oh my god. Give me the it's mine. They don't know what's in the tin. I'm literally just gonna go home and do the
Haven't blown out your candle. You probably need to blow out your candle.
No.
What's floating in it?
Is it cereals? They're ours.
go home and you go to the
Okay. Only fill one of them with water right now. Now, the reason I had to only fill one is that way, even if nothing's in the other one, you're not going to go over. Now, I want you to pour some of that water into the other bucket. Get everything out of the bucket. I don't want them to be equal. I want them to be different levels. I need one person in each group to get a computer.
I got you.
Do we
Give it up.
fill this water or? Very good.
The person who's got the computer, I need to get into Excel.
Oh, I scared. I'm gonna like.
Excel was not my
Everything
favorite.
on
I could do PowerPoint, I could do Word, it was just Excel.
Now, if you are not a fan of Excel and nobody in your group is, then there is a paper version of what I want you to do here. And you can set up a graph and record everything here. So, if you want to do it paper-wise and you want to make a graph, you should go, you can do it that way. So, you don't want to use Excel. Okay, listen please.
What is your bucket weight?
Your bucket thinks we've got a problem.
Yeah, weight.
Okay, come get another bucket. Okay. So this really takes a minimum of 3 people to do. It really does. If you've got 4 in your group, guys, if you've got 4 in your group, it works really well because one person is in charge of the reactant and writing down everything you do, and the other person is in charge of writing what down the product does. What the product person does. One person needs to be in charge of the reactants, one person needs to be in charge of the products. Okay, so you want the buckets right next to each other, the people that are doing the product and reactants need to be right next to each other. You need to have a ruler down in each of them. Make sure the 0 is down, not up. Excel, you want to have 3 columns and they're the same as here.
No, you best be joking.
See guys, I'm starting to lose my voice and you need to be quiet so you can hear. If you've got your computer, you're doing Excel, you need to set up 3 columns. Trial number, reactant, and product. Okay, now.
Anyways.
Okay. The people that are the product and reactant people that are not doing the writing down are going to be right next to their buckets, right here. You're going to have this up and this up. You're going to take your large beaker and your small beaker. I would like the reactants to be the small beaker. The products to be the big beaker. So you decide which one is which. Okay, you are only in charge of 1 beaker. Now this is important. You cannot tip your buckets whatsoever. Not tip your buckets whatsoever. You're going to dip down into one if I'm the reactants, and I'm going to dump it in the other one. Product person's going to dip down in theirs, and they're going to pour it in mine. We're going to stop. We're going to read what the height is and give it to our respective persons. They're going to start graphing it for us. Okay? You're going to do it as fast as you can. We're going to try and get to an equilibrium where we have a 0 slope for the same number in both the reactant and the product, different numbers but the same number on that side, at least 3 times in a row. You have 5 minutes. Go. No, whatever the reactant is, that's smaller. So just
Just how
So start first by taking your initial reading. What's your initial reading? Reactant is dismissed. You guys decide which is it. So you should have a ruler in each pocket. Does everybody have enough rulers?
So the product was green chips, 7.
I mean, that's 2 different buckets, right? Yeah, I don't get to keep it. I
As fast as you can, right?
But you gotta take a reading in between.
I'll take a reading.
Oh, we're doing
8 for us.
So remember, you should be reading in centimeters or millimeters.
I think so.
They were.
Perfect. So we agree.
Be done with that.
Okay, you should be doing this. Tell me what's happening. You got about 2 minutes left. So the person recording it should be either recording it and or making graphs at the same time.
Oh, that's not bull.
So guys, you should have 2 lines on your graph. You should have one for your reactants versus trial number, and one for your products versus trial number.
That's impossible though.
And we're taking more out of this. This is why I said this
They don't make sense.
I knew something was wrong with me.
Still the same.
I told you.
Okay, guys, you're looking for when you hit a 0 slope. You're not looking for where they cross. You're looking for when it hits a 0 slope. It changes. Okay, buckets can't move. Buckets can't move. You have to dip as much as you can with the beaker. Some of you got the brass running as you put the stuff in. That's a smart way to go. You got your count, yeah, until you get a 0 slope. Okay, that timer's already went by once, so we're just going to give you another minute. Ooh. Yes! Yes! Got one good guy here? There's one up front that almost got over here on that side. Just keep tipping. What did you get on picture?
It doesn't matter.
It started off like
So you're going
ours is more than
But we also.
so they're never measured. It's like
It'll get to the point where they're the same number. They'll stop and read. Don't put your water back in. You can only dip once. Okay, you guys reach. Okay, go ahead and clean up. If you reach it, go ahead and clean up. Put your stuff back over the dragon box. Dump the water out.
Oh.
Okay.
Oh my.
Are we turning this in?
Okay, so let's go ahead and clean up. I wanted to show. Those of you that come on the computer, keep your computer out so you can show somebody next to you what you did. But basically, yes.
I don't know how to sell this.
You take, did I wait parts that
Yes. What you're missing.
It's due January 15th.
Everything is due. Whatever you're missing. Anything from chapter 1 on. Okay.
It says like you have to change your password. Does it tell you like
Remember? You have to change it. I just add a 1 or 2 or maybe 3 or something at the end of the whole password. So keep it going.
and then does it let you change right here? Keep saying the last name
Next, what do we do?
Okay. Yes, make sure you take a final weight on your candle. We'll be working with that more next time. And then put your candles back up here for me, please. We're going to talk and finish this up so we can have a final. So quickly, within the next minute, please find your seat.
I don't know how to do
Candles are right here. The scales are in the box. Okay, so we're going to work with this next time in capital 1, so don't waste it, because we're going to do these calculations. Have a seat real quick. We're going to talk about equilibrium and Le Champlier's cycle. Okay, if you did this correctly, and there was a big if for some of you, okay? You should have had your reactants start up here, and they should have done something like this, where they finally ended up with a 0 slope. Okay, your products should have started down here with a 0, or somewhere above 0, with some smaller amount, and it should have ended up here with a 0 slope. You're looking for a slope of 0 to be equilibrium. You're not looking for where they cross. Okay, so then I would look at this and say, oh, the first part there, probably both of equilibrium is somewhere right there. And I would look at that tile number, or I would look at that time, and that's what I would write down. You need to be able to read that off a graph. Okay? What do you need to be able to read off a graph? What is equilibrium?
When the slope is 0.
When the slope is 0. It's not when they're the same. Yes.
So when it says like what is the equilibrium, you write down the time that it's
The time, yep, right here. Okay? So she will put this point on there. She will put that point on there. That is not equilibrium.
that's the intersection point where they meet.
That is where they are the same concentration, but it's not equilibrium. Okay, so you need to make sure you understand the difference. She will put several other points in here. That's almost equilibrium, but it's not equilibrium. Okay? Shh, guys.
Is it like calculations, or we just like look at it and it's like, oh, this is where it's at 0?
So if she gives you a data table with information, what are you looking for?
We're looking where the slope equals 0.
Where the same number is 3 or 4 times. Then you know you can equilibrium. Okay, guys? I'm going to put in a plug again. One more time. You have all of Christmas break. You have got to get all your notes, all your homeworks done. Okay, it's 20% of your grade. You've got to get me your labs in. That's 20% of your grade. That's a total of 40% of your grade. If you haven't turned in any learn smarts or homework, that's 20% gone right off the top. You're now down to 80. If you haven't turned any labs in, that's another 20% gone. That takes you down to 60%. You can't pass. Okay? You've got to do your homework. You've got to do your labs. If you're having problems, get your butt in here, sit next to me, let's work on it together. You've got to get it done. Okay? I'm here to help you, not penalize you and cause you all kinds of grief. If you were in a regular not CE class, but 11-10 class at the college, you would have to have them done the Learn Smarts by the first day that they talked about that in class. You don't have a second chance. By the time you finish that chapter, the homeworks are done before the test. And guess what? It's 12 weeks. We cover 13 chapters. Guess how many days on each chapter? Yeah. So it's one. Of course, you go to the testing center, not in the class, but it's 1 to 2, possibly 3 days on a long one. That's it. So you got to really pace yourself, get it done. You guys have got so much more time than they have, and there's no excuse for you not getting those points. I'm going back and looking at kids that haven't done Learn Smarts. Really? All you have to do is do them. You get 100 points. This is a duh. You know? I'm getting a little frustrated because you should be easily up, even if you get your labs at 20%. Because guess what? You can return them in. If you don't get 100% on them, get them back in. Fix whatever's wrong. Return them in. I'm letting you do that. You should have 20% in labs. Homework, yes, ma'am.
Can we return our homework in? Like, 'cause you said you opened it. So
I opened it. I don't think it lets you get back in it. She sets those limits. Okay, there's one that you get 1 chance on. There's another that you get several chances on. If you're down to 3 chances or 2 chances, whatever it is, and you still haven't got it, come sit by me. Let's get that problem right. Okay? There's no reason why you shouldn't have at least 15% in homework and Learn Smarts. So there you got 35. 70, below 80 is that B- threshold. So you want to be above 80. That means you got to at least get 45% on your tests. Come on, guys. You know, I don't know what else to do for you. I'm begging, I'm pleading. Do your homework.
Extra credit.
And do your labs, okay? No extra credits. That's one thing they won't allow. Okay? All right. Any questions? Yes, ma'am.
So what happened with the test? The chapter 5 test.
What happened to it?
When I got my test score back, it was at 58, but it says it went up from there.
I was able to talk her into a few points because of a couple of questions.
Okay.
If you see it raised, that's okay. Experiment number 11. Experiment number 11. When we come back, make sure you got the 3 labs and the data tables ready to go when you hit labs. Okay, we'll see you on Friday, right?
Yeah.
you were showing me to sound like you
No, I'll be here. Today was a half day. I had a half day sub because we did.
I was gonna say unless I'm like
11. It's a Thursday.
I'm pretty sure we did our lab round because we got
Okay, again, I have got it set up. If you want to do silver and gold, we're going to do them next time. We're also going to do silver test tubes. So the